Hi everyone, I'm Jeremy and I'm one of your ENGG1100 tutors, and I'm here at my desk today to show you how to solder. Okay, so first let's talk about why on earth we'd want to solder. So most, in fact all electronic circuits need to have more than one component in them to do something useful. I guess that's why we build circuits. We have lots of little configurable pieces. So when you've decided that your circuit works, you want to basically glue everything together in place so you don't have to keep fiddling with it and it doesn't move around and it's strong and all those other things. So basically what we do is we get a bunch of components. So I have a few here. This is resistors, transistor, LED, and this is an integrated circuit. So this could contain lots of all of these three things. And what we do is we get something that has holes in it, like this. They're usually a standard size. They're 0.1 inches spaced apart. And then what we do is we arrange our bits in the holes, like so. So I'm obviously just making this up. You don't necessarily have to put them in this way. So that's all well and good, but if I do this, they just fall out again. So what we need to do is do what I guess call metal gluing, and then you get solder. So let's have a look at this. This is ECG, so the kind of thing that you go to the hospital and they stick a bunch of things on your chest and then they look at your heart through electrical signals. That's what's, I guess, this is one part of what's in them. So you can see, if I zoom in, hopefully it focuses. So we've got lots of components, some resistors, some of these ICs I talked about. There's a capacitor, another capacitor, more capacitors. You can get huge ICs. You can get ICs that need you to suck the heat off with this big heat sink. You can get all connectors. So there's plenty of things you can buy to build your circuits, but the important thing is here. So let's see how close I can get this. Nope, doesn't like it. So basically what you want to do is get a component and form an alloy using a special metal we call solder with the component leg that's being poked through the hole. So if we look back at this one, you'll notice that there is already a silvery metal on the holes. When we put a component through, what we want to do is put solder so it bridges mechanically and electrically between the hole and the component. So I just need to mention one thing really quickly. Nowadays electronics is getting smaller and smaller and smaller and smaller and smaller. So you come across what we call surface mount components. Now you've got to be very careful when you buy things from, say, Element 14, because they might ship you these. Now they're actually really tiny, so if I put this in there, you can see that the pins are not spaced at 0.1 inch. There's a lot more pins in there than will fit. And we call them surface mount because the pins don't go through holes. Now, these are really useful if you're making something like this. This is an audio processing unit. But you can fit lots of things all on one little board, and that makes sense for economics. But for us, it's really hard to solder. So we're going to stick with what we call through hole. So let's talk about tools you need. The first and most obvious one, I guess, is a soldering iron. This is mine. Yours might look a bit different, but they all do the same thing. You need some kind of circuit board. So this is what we call a perf board. You can get all different shapes and sizes, keep lots around. And this lets you solder things in. It's a place for everything to stick together. You need your components. Let's just say we want these two. and you need some solder. So here's my big roll of solder. Now, the types of metals in solder mean that it's not necessarily that cheap if you buy a lot. So this roll here is probably worth about 250 bucks. It'll last me forever, but you just need to be careful that you aren't wasting it all on nothing. And the last thing is what I'm playing with in my hand here, blue tack. People don't seem to realize how useful this stuff is, but you can stick your board down, and while you're soldering, then it's all good. So anyway, let's get on to soldering. Oh, and one more thing. Safety glasses. Really important. Okay, so let's talk about actually soldering. You want to turn your iron on to about 370 degrees. It's important to remember that the temperature you turn it on doesn't change how fast it heats up or necessarily how well it solders. That's to do with the wattage of the iron and not the temperature you set it to. So once it's heated up, it might have like a little light that starts blinking. Then what we need to do is, before we tin it, we need to turn our fume extractor on. So I have this blue one here. You might have a black one in the labs. But basically the fumes that come out of this they're not lead, because lead doesn't melt at these temperatures, but there's a flux core in most solders, and that gives off a bunch of smoke, and you don't really want to be breathing that in because it's not good for you. But let me try and zoom in here. So the first thing we want to do is tin the tip. Basically this sticks a bunch of new solder onto the tip and removes the oxide layers that have built up while no one's used the soldering iron. If you're using the soldering iron straight after someone else, you probably should still tin it just because you don't know how good a solderer they were. So you just get a lot of solder on there. Should have like this big ball of it. And then your tip goes nice and shiny. Hopefully you can see that. So I'll just do it once more. Yeah. So you know your tip is well tinned when the solder is quite wobbly on there. Right, so now we're ready for business. This thing is fixed in place, can't move it. So what we're going to do is find a pin, like here. We're going to heat up both the pad, that's the bit on the PCB, and the pin of the component, and then we're going to push solder into it. So it's a bit hard to do behind camera, but let's give it a shot. So you can see that it looks kind of like a little tent. That's a good solder joint when it looks like a little tent. So I'm just going to go ahead and do a few more. Now if you find that they're not really coming out like tents, they're coming out sticking to one, maybe the PCB only, or sticking to the leg only, there's a few things that could be wrong. The first thing is you didn't tin your soldering iron, or you need to do it again. The next thing is that you set the temperature wrong, or the iron isn't at the right temperature. The last one is a bit more annoying, but the components themselves can oxidize, the legs on them and the PCB as well, and it's really difficult, it's not really possible to solder to something that's oxidized heavily. So what you may need to do is get some sandpaper and just rub it over very lightly over the parts that you're trying to solder. So when you're done soldering, you should wipe your iron. Maybe you've got a sponge, maybe you've got like this golden steel wool. Either one is perfectly good. Just wipe the solder off, and then put it back in your holder. There's no need to turn it off while it's in the holder, unless of course you're going away from the iron. But let's try and take a look at this now. So this component is not going anywhere. I can get some pliers and try and rip it off, but it's not going to happen. Yeah, I'll probably snap it in half before I take it off. And if we look under here, I have lots of these little tents. Now, I would probably put more solder on these. I'd say this one is a very good one. Maybe put some more solder on these ones. But really we're looking for mechanical strength and electrical connection. So you can see that the pin has been alloyed to the board. So that's good for mechanical strength. And because there's no gaps in it, we know that they're also electrically connected, which is what we want. So now, let's do an LED. So that's this guy right here. So, same thing applies. We stick it through, but it's a bit wobbly. So what we want to do is hold it in place and bend the legs in opposite directions, so that no matter what we do, it's not going to come out. Now we get our good friend blue tack, stick it in, and go for it. Cool. So the last thing we need to do with a component like this is get some side cutters and take these legs off, because if we let them poke around, they're just going to touch other components in the circuit. So I don't know, it may have been bent like this and it'll touch all those pins, and we don't necessarily want it to touch those pins. So get some side cutters. You'll normally notice that one side of them is flat and one side of them has like a cutout in it. So here are some other ones I have. That's obviously the cutout side and that's the flat side. So you want to take the flat side, put it the same side as your solder joint. See if I can do this. And then cut it. Same thing goes for the other side. So you want to try and get these legs that remain as short as possible, because you really don't want them touching other parts of the circuit. So having something like this is all well and good, except these two components aren't electrically connected yet. You know that this metal plated hole is connected to this side of the LED, and the same for here and the same for these guys. But in a circuit we maybe want to connect this one to this one and this one and this one to this one. It really depends on what you're building. But the way we do that is we use wires. Now, I could probably talk about wires for several hours, but very briefly. This is wire. This is wire. More wire. More wire. So wire comes in all different shapes and sizes and insulations and current ratings and who knows. But what we're really interested in is the two types of wire. There's single core, which means there's a single strand of copper. So this is single core. And multi-core, which has multiple cores of, it doesn't necessarily have to be copper, but a metal like this. So the benefit of using multi-core is that it has a lot more mechanical strength and it's a lot more flexible. So when you're fiddling around with your robot and it's driving around and maybe the wires bend up when it turns, this multi-core stuff is sweet. This single core stuff, not so good, because if you bend this enough, it will snap. And it holds its shape a lot more. So you'll note that I've just put this annoying little knot in there and every time I try and straighten it out it gets closer and closer to breaking. So avoid the use of single core wire except for when you're plugging wires into your Arduino. That's really important. So I lied slightly. Another place I'd use single core wire is on a PCB if I wanted to connect that pin to that pin. So let me get some and I'll show you. So here's a piece of single core wire I got out of a network cable. You can see there's only one piece of copper in there, and it has the same problems as the other single core. You can see that it's already a bit wobbly because of the way they wind the cable, but for the purposes of this we don't really mind. So I've pulled the insulation off both ends using my, sorry, that's my pliers, my snippers, and I'm going to get on this side of the board, zoom out a bit, and what you want to do is put it through the holes next to the components that you want to connect, like so. Now you don't actually connect anything by doing that. On this side of the board, what we need to do is solder these new wires into their holes. That's the first thing. So I like to bend them so they don't fall out. Put it on the blue tack. Get your soldering iron. And solder it in. It's not going anywhere. Now what you also want to do is join these two things. They're not actually joined, it's just the camera angle. So we basically, to do that, the easiest way is just put a bunch of solder on. So let's give it a shot. Now the solder's not really sticking to my tip, so that means it's time to tin it again. Nice and shiny. So we just put a whole lot of solder in here. It's important to heat both joints because otherwise the previous one won't melt. And you can see now these two holes are electrically connected because there's no gap of metal between them. So if we want to connect these two, same thing. Now it can be a bit tricky depending on how well the components take heat away from your joint, because obviously if you start heating up the joint with your soldering iron and then the metal conducts all the heat away, your solder alloy is not going to melt. So here we have this stupid circuit. It's not going to actually do anything because I didn't plan it, but that's basically the idea of soldering. You can stick things so that they mechanically stay together. It's almost like gluing, but at the same time you have electrical conductivity. Now a few things to go through just before we're done. This is what we call lead-free solder. Now originally solder was of the leaded kind. So it says here 60% tin, 40% lead. Now the reason they use lead is because it's really malleable. I know you can't feel it over the internet, but this one is a lot softer and it'd be really easy to break with your hands. Whereas this one, I can only really break it because it's thin. This one is actually made from, it's SN100C. It's not actually 100% tin, but everyone seems to have their own combination of tin and bismuth and antimony and all sorts of strange metals. The reason we use lead-free solder now, although you may still come across leaded, is because in the EU selling a product with leaded solder without a license from the organisation is actually illegal. They don't want lead to leach into their waterways. It's a bit controversial. A lot of people don't think that lead-free actually does anything better because you're just changing the heavy metals you're using, but that's beside the point. The only thing you need to remember is if you have lead-free solder, you probably need to solder at about 370 degrees, but if you have leaded solder, you can probably get away with closer to 300, 320, and lead-free solder tends to not have shiny joints, so you can see these are quite matte. Let's see if we can focus it. They're shiny, but they're not super shiny. When you solder with lead-free solder, they'll come out really quite shiny, and lots of people on the internet have pictures up saying that if you don't have shiny joints, they're bad. With lead-free solder, that's not actually true. So lastly and most importantly are your hands. When you finish soldering, you need to not touch the components you've been soldering. The reason I use blue tack, other than holding it down, is because I can't hold it, it will burn me. And I have burned myself plenty of times soldering, and it is unpleasant. So when you're soldering, don't touch what you're soldering, don't get your hand too close to the joint. Remember that metal conducts heat, so if this board has a bunch of metallized holes, then the heat is going to be conducted away, and if you're holding it, you'll burn yourself. The other thing is, the metals used in this, particularly the oxides that come out, and that smoke that you saw coming out of the solder, none of those are good for you, so you need to be careful. It's safe to do with bare hands, and I suggest you do use bare hands, but afterwards you need to wash your hands because you don't want to be eating this stuff. And particularly, you're welcome to smoke, that's your own life choice, but particularly don't smoke after soldering if you haven't washed your hands, because some research suggests that the barrier to lead going through your lungs is reduced significantly when you solder. So yeah, that's just a few other safety things. If you have any questions, feel free to put them up on the Facebook group or Blackboard or something, and I'm sure someone will get to help you.